This video will demonstrate Maitrix's error-correcting tensor processor unit, also known as the ECTPU. Maitrix's ECTPU is the world's first error-correcting matrix arithmetic processor, combining advanced residue number system architecture from our RNS TPU product with breakthrough forward error correction of arithmetic. Unlike traditional approaches that detect faults after the fact, forward error correction of arithmetic enables real-time correction of arithmetic results, even during active computation. Designed to survive both transient and permanent faults, the ECTPU redefines what's possible in high reliability numerical processing. Now, let's move over to run the demo. We will go ahead and, starting with our Visual Studio Code C program, we will go ahead and launch it. And what you see here is a C-based application that's accessing our error-correcting TPU that resides on a Stratix 10 FPGA. The Stratix 10 FPGA from Altera is large enough, in this particular case, to support an 8x8 matrix multiplier. This matrix multiplier is fully systolic. It allows us to multiply a matrix in 9 clock cycles on a continuous basis. The precision of the matrix multiplier is a 32.32-bit signed precision. That precision is a result of running 10 18-bit residue digits, which you see in the middle of the screen as very small tiles. Those small tiles, each one represents a digit of the residue number system. To the left, we see the overall result, and we see that the grid is all green. And the reason for this is because we haven't injected errors into the residue number matrix multiplier yet. So this demo will demonstrate how the system will detect the errors and in most cases correct the errors. This particular forward error correction of arithmetic corrects a single digit error in a single RNS word. So it doesn't matter how many matrix dot accumulations have transpired. It doesn't matter how many product summations on a particular dot product is actually executed. If a particular digit is an error, that digit will be detected and corrected. So let's first start out by noticing that what we have at the top is two white matrices, and they're shown in floating point number format. And this hardware accepts single precision floating point numbers, converts them into a 32.32-bit precision, and then multiplies those two matrices and outputs the result in floating point. Note that the entire matrix computation, however, is done in the residue number system. And the reason why we want that is because there's no carry between digits in the residue number system. This allows us to run essentially 10 matrix multipliers in parallel. Each of those 10 matrix multipliers only focusing on a single digit. This is only possible if you have a carry-free number system when you're computing the matrix multiply. Furthermore, if an error is trapped in one of those digits, because we are computing with a carry-free number system, there's no chance that that error will propagate to other digits in that word. That's one of the powers of the residue number system, and this is why we can do extremely highly accurate product summations at breakneck speed, and on top of that provide error correction. Let's first start out by injecting an error. We're going to go ahead and inject some dot errors, and we do that on our key menu on the blue on the right by basically hitting the P key, and that will actually toggle our dot errors. And so the dot product errors are single errors. Now we notice that we're seeing some yellow checkers on the left, and occasionally we're seeing a red ones fly up, and in the middle we're seeing the yellow dots in the error digits. or in the digit matrix multipliers for each digit. So I'm going to go ahead and slow this down so I can explain it a little bit better. So we'll hit the R key and that'll put us into a single step mode. So as you can see, if the tile on the left is yellow, that means that an error was detected but corrected. And you might ask, where is our errors coming from? In this particular demo and with this hardware, the FPGA supports error generators, and so this is how we're actually simulating errors. These particular errors are focused on the dot product themselves. So as the dot products leave the matrix multiplier, we insert an error and then we detect it and we can correct it. Additionally, the architecture of this particular matrix multiplier is such that there are 8 readout ports on the matrix of this systolic matrix, and so therefore we're actually supporting 8 parallel error correcting units. So this particular unit can correct errors on a continuous basis while it's multiplying matrices every 9 clocks. The matrix multiplier in this particular FPGA is running at 300 megahertz. So as I press the space key, you'll notice that different errors are being injected for each matrix multiply. And notice that in this particular case, on the left, we're seeing a yellow on the column 4, row 0, but we see that over in the middle of the screen, the digit 5 here is actually where that particular error occurred. So as I continue, this one didn't have any errors, so this particular run, I'll go ahead and hit again, and now we see this bottom at column 4, row 7 has an error, and that occurred in the digit 0 position. So you can see that we're tracking exactly where the errors are occurring. In some cases, we can see that there's multiple errors. So in this particular case, on the left at column 5, row 5, we have an error, and that was because digit 7 was an error, and we can see that here in the middle. Furthermore, at columns 1, row 6, there's also another error detected, and that was because digit 9 down here had an error injected. And in this particular case, these errors were not only detected but corrected, and this is why they're painted yellow. Remember that in this particular case, the error correcting unit corrects a single digit in an RNS word. So it can detect an error in a RNS word with two digits in error, but it cannot correct it. It can correct a single digit in an RNS word, both detect and correct that. So we will show that a little bit as we go. So here, as I continue to advance the demo, we see different errors coming up. And in fact, this demo allows me, see here we've got 4 different errors, and coincidentally they all came from the digit 5. This is a random process here, so the error injectors are random, actually pseudo-random to be more precise. And we can actually increase the probability that an error will occur by another key that we support in this demo, and I'll go ahead and do that. So we'll go ahead and increase the probability that errors come up. Now, interestingly, we now see a red tile on column 2, row 7. In this particular case, there was more than one error in this particular dot product. So there's no way to know in this particular case which digit was an error, and that's why you see a red in every single one of the digit matrix multipliers in the middle. So each digit here, in the case of the red dot product, is being flagged. We just don't know exactly what digits are in error. However, for all the other yellow ones, clearly we do know what digit these were actually injected into as far as the error. And once again, if the tile was on the left was yellow, an error was detected and corrected. If the tile is red, the error was detected but not corrected. So we'll go ahead and continue to advance this, and because the error rate is so high, I've got it set so high that obviously there are times when two errors are injected into a single word. In this particular case, we've got two particular errors that were detected that were not corrected. We've got many other dot products where errors were detected and corrected. So let me back off on the error rate a little bit here and get that back to a little bit more reasonable probability. And when I run, you can see that get some feeling for what it's like when matrix multipliers are being executed and while errors are being injected. Okay, so we will go ahead and go back to single step mode. Now I'm going to go ahead and turn off the dot product errors, and I'm going to go ahead and turn on row errors. In our demo, if I hit the E, you can see that row errors are now enabled. So now as I single step through these, well, I'll have to increase my probability of these errors, and that's down here. Right now my probability is set to 0. So I will go ahead and increase the probability for row errors. What is exactly a row error? Notice now on the left we have an entire row that's all yellow, which means that the matrix multiply was still successful, but we detected an error in every one of these dot products. Well, this is the type of scenario that can occur in a high-speed matrix multiplier when the readout of the data coming into the matrix multiplier is in error. And so, as you can imagine, because matrix multiplication involves row times column product and then summation of that product, even one error in the readout of the data coming into the matrix multiplier could create an entire row or an entire column of errors. And this is not really obvious when you first get into matrix multiplication error correction, but this is a very possible error mode. So as I single step through here, we see that multiple readout errors are occurring, and I'll go ahead and set the probability that these are occurring at a much higher rate. So now we see them at a higher rate, and we can see in this particular case even multiple readout errors are occurring, and these readout errors are affecting an entire row. In this particular case, we have two rows that were entirely wrong as far as an error, but because the error was only in single digit in two different cases, the errors were able to be detected and corrected in real time. So again, we can single step through. I'll go ahead and increase the probability even greater to the point where now we're seeing some red bars. What does the red mean? The red means that a readout occurred, but the readout was actually more than one error. So 2 digits of error on a particular word, or any of the words read out for the row, would create a 2-digit error. And so that 2-digit error is being flagged as all red. And in this particular case, we could detect that the matrix multiply was an error, but we could not correct it. And so as we go, again with a very, very high error rate, we can see some of the different patterns that are being formed. Okay, so now let's move on. I'm going to go ahead and back down the probability that these errors will occur to something a little bit less, because what I'm going to do now is I'm going to turn on column errors. So here, go ahead and cycle through this, and now I can show you column errors. And so for column errors, it's exactly the same situation. In this particular case, the second matrix that was being read out is now in error. And let me be clear, the second matrix of the input of the matrix multiplier was an error, and this is causing row errors. And you can see that this is a random process, and obviously row errors come up. And if I increase the probability that these errors will occur, then the same situation will occur here where we've got red. In this particular case, when we read in the matrix, more than one digit of this particular column was an error, and that causes a 2-digit error in all of the dot products of the matrix multiply. Now, interestingly, if we go ahead and turn row and columns on, and let me go ahead and turn this probability down, we will start to see what happens when you actually have a row and a column error at the same time. Here's a good example. In this particular case, we've got column 1 all in error, and we've got column 4 all in error. And the forward error correction can correct most of it, but it cannot correct where the row and the column intersect in most cases, simply because the chance is very, very high that for that dot product at column 1, row 4, which is here of course, there's 2 digits in error for the dot product. And therefore, when you have a situation where the column readout and the row readout are both an error, then you will, in many cases, get an error where the intersection of the two occur. The times where you would not get an error is if coincidentally the same digit is an error. In that case, it only would result in a single digit error correction, and then in that case it would be corrected. Maitrix has the technology to also correct for this, but that will be in a future demo when we finish up the correction circuitry for 2-digit errors. Again, I will just go ahead and run this and run it at a little bit faster rate, and then you can kind of get some idea of what it looks like when you have readout errors and you're actually correcting and detecting errors. Now keep in mind the detection of an error, even though it's red, is still very valuable, because you could create a circuitry that would just simply rerun the same matrix. So it's very possible that even with single-digit correction, you can still have very high performance of corrected matrix products simply by rerunning those matrices that were not fully recovered. Now I can go ahead and combine the row and column with single dots. And now you're seeing really just a barrage of different errors that are being thrown at this matrix multiplier, and how the system can actually correct for it or detect that the matrix needs to be rerun. I'll go ahead and go into single step, and we might find some interesting patterns here. But as you can see, in some cases you will have a double-digit error, and it's not exactly always obvious when those errors can occur. But detailed analysis will lead you to believe that there was a double-digit error in that particular dot product. Okay. All right. So to learn more about Maitrix's error correcting TPU, come to our website and go to Technology and select Error Correcting TPU. And the Error Correcting TPU webpage has a little bit more information about different applications for high-speed matrix processor with error correction applied to it. If you're interested in any more of this technology, please reach out to Maitrix. You can reach out at info@maitrix.com. Thank you. Thank you for your attention to this advanced demonstration.